thanks for coming. So I think you have a good idea why we're here. So last time I showed you a few ways of how to deal with parametric design, especially relating to construction communication, drawing output, schedule output, things like that. And in my case particularly, using Grasshopper and our own plugin Elefront. Now I only showed you what it can do and how we use it, but I did not show how you can use it. And that's why you're here. So it's not going to be like a lecture, really. It's not going to be a PowerPoint slideshow again. As you could already see for a little bit, I'm just going to try and do it as a live demo to show you how it works, where it goes wrong, because it always does, how you can fix it. And then, because you're such a small group, which is kind of nice, come on in. Since you're such a small group, I think there are going to be a lot of questions, and I'm going to try and just deal with that. So if you have any specific things that you want to know for your project maybe, then you can just ask me, and I will try and just show a couple things that may either change your life or make your life a little bit easier. Hi guys, come in. So as a quick recap, what I talked about last time is basically when you're dealing with any kind of automation, programming, parametric design, algorithmic design, you basically work within the same logic over and over again. You have something that you want your automation routine to do, to perform. And in order for your automation to actually do that, it needs inputs. And then when your automation is done doing whatever it's doing, it will output something. And that's the same thing over and over again. Now, what I showed briefly last time is what I'm going to start with today as well, is how can you use inputs to get outputs on a building scale. So basically your function is going to be, in this scenario, is going to be a Grasshopper definition. And it's going to perform. It's going to do something that you intended to do. And the inputs are going to be models in this case. Primarily it's going to be models. And the outputs are also going to be models. And it can be also drawings, it can also be schedules in this particular example, and we can see where that gets us. So I showed you last time, if you have an envelope and you subtract some shapes from it, you can have a modified envelope. And if you have a modified envelope and you have some grids, then you can have the panelization of, in this case, your facade. And if you have the panels of your facade and an elevation from the architect, which will contain different types or different annotations on those specific panels, then you can project that information onto your panels, and that way you can enrich your model further and further. So to stick with the input and output example, basically in Grasshopper the output is mainly whatever you bake back into Rhino, and your inputs are basically whatever you're referencing in from Rhino. That's the basics. Of course you can have all kinds of inputs. You can have inputs from Excel, or you can have inputs directly through a plugin, directly coming from another application. We may even touch that, but in this scenario that's kind of the main idea. So we've talked about attributes. So in order to get a meaningful schedule, or in order to get your function to perform the right actions on a piece of geometry, you may want to know more information about that geometry. So for instance, if you're going to extrude a curve in order for it to become a surface, you would want to know in which direction to extrude the curve. Now, for instance, you can store that information already inside the curve. So the curve will then inherently already know in which direction it should be extruded. Now, if you have 5 curves and they're all extruded in the same direction, that's, of course, it's not a very sensible thing to do. But if you have a model with 10,000 curves and they're all in different directions and they should all be extruded in different direction, then all of a sudden it makes a lot of sense. So we're gonna look at that as well. So we've seen this project. I'm not gonna do this project. I'm not gonna show it. I could, but it's a monster. So we may not like get through it tonight. So I'm just gonna show a simplified version of the same concept, basically, which is what I've prepared for you guys over the weekend. Somehow the slides progress like very slowly. So we've seen this like close-up attributes on panels, how to export a schedule. That's what I will show you. And I think this is no longer part of alright. And then we may even touch how to like create more detailed geometry based on more simplified geometry from previous steps. And as I said, we will also have a look at drawing generation, because that is something that you guys are going to be doing, and you could make this a great opportunity to impress your teachers and your tutors at your reviews, and have some like very detailed schedules of the elements in your building. And this is really like, this is day-to-day practice. People need to make this stuff. This course is about how do you inform people about how to make this stuff, and you can really win a lot of time and effort by automating the process into creating all these documents for you, because whoever drives the model and whoever drives the output basically drives the design. So this is a great opportunity for you to really control what your building will look like in the end. Because if you don't specify it, then the contractor will just do something. Alright, so let's have a look at our Rhino definition here. PowerPoint just messed with my screen settings, which is alright, no problem. So let's start with the start. So basically, like I said, what I'm going to do is I'm going to try and reproduce the example that I just showed you and take you through it step by step. So as I showed in that example, we have a envelope, which kind of like it relates to your massing model, right? It is basically just a massing model. This is the exterior of your building, and this is what you're going to work with. Now, the massing model is not just a separate model. The massing model can be used for you to augment your model, to get more detail into it, apply more detail to it. And with a parametric system, with an automated system, basically everything can be related back to previous steps. In this case, the envelope is kind of like the first step. But if you were to modify the envelope, you are to modify everything that's dependent on it throughout your automation routine. So that makes it relatively easy for you to make changes and updates. And if something went wrong, you can go back and just fix the one thing that went wrong, and everything that was good, you can just like keep it. That way you don't have to redo your model over and over again. So this the screen is like really small because the resolution of this projector is like medievally low. So I apologize for that. I'm gonna have to like try and scramble everything inside these 1024 pixels. It's just a little bit painful, but let's just see where we can get that. So I have an envelope here, and basically I believe I modeled this by hand, and I made sure that these facets are on a layer that has a meaningful name, because not only can you assign user-defined attributes to your objects, but you can also use common Rhino attributes like a layer and a name and a color. So whatever Rhino attributes you assign to an object, you will be able, using Elefront, you will be able to read these attributes from the objects again. So in this case, I placed these surfaces on a layer that I called envelope Y, and I did that because it kind of indicates that whatever gets like placed on this surface should be oriented along the y-axis. Now there is also these surfaces there on envelope X. Same thing. Whatever is placed on these surfaces should be oriented in X direction. And then there's this guy here, which is called envelope radial, because everything that this surface is relating to is basically in a radial direction. Now the reason why I did, and I gave these names. So I gave this one the name facet 2, and I gave this one the name facet 1, 3, and so on and so forth. Now as you can see, if I were to like drag this stuff, it's not really moving. That is because I brought this model in as a work session. Are you familiar with work sessions in Rhino? Not familiar with work sessions. Now, if I have an empty Rhino file, like this, I can take any model, drag it on here, and then I will have some options. So one of the options is to open the file. We'll just do that. Insert the file. We'll basically insert it as if it were a block, so you get to like pick a point and it will place the model there. Import the file will basically just import everything inside that file once at the same location where it was in the original model. That's it. And then there's attach file, and basically that's the most interesting option as far as I'm concerned, because attach file will basically bring in everything that's inside this model, but it is not really a part of this model. It is a reference. So like in AutoCAD, you probably know like external references. It is kind of like an external reference, but with the nice difference that you can still select objects and deal with objects individually. Unlike an external reference, basically in AutoCAD, if you select the whole thing. But here you can still work with individual objects. Now, if I were to pull the properties of this guy, you can still see what layer it is on, what name it is, and if I were to like section this, I could actually perform operations on these objects. And my section's here now. Now, the result of this operation is placed inside the active model. So if I were to remove the work session from this model, work session. So this is the work session manager, and I will remove this guy from here. And then the result of that operation is still there. So now I have a new model with very clean geometry, and it only contains the section of that model that I just brought in, but it's not really a part of this model. So that's a work session. So I did that here as well. So this envelope is basically the model that I just showed you referenced in here. And what I also have is another model that represents the grids of this building. Now also these grids are placed on different layers. This is the grid in the X direction. This is the grid in the Z direction. And then there is a grid that is a radial grid. So you can kind of already see that we're going to use these properties to mix and match the grids to the envelope surfaces. So when we have a look at the grasshopper file that I prepared, basically what I start off by doing, so let me spoil it for you. So the result of this operation is going to be I'm going to split the surfaces of the envelope with the grid lines in order to get the panels, in order to like work with it. So in order to do that, we need to bring in these envelope surfaces. So using Elefront, I use the reference big component. Now, what I told you in the last lecture, can you guys all hear me okay? There's no problem? No need for the microphone? Okay, cool. Whenever you use a big component in Elefront, so let's just like take it one step at a time. If you have installed the Elefront add-on, you'll get this tab, and there's a whole lot of tools there. And one of the most important tools is the Bake Objects tool. And basically what it allows you is to feed it geometry, to feed it attributes that belong to this geometry, and to feed it a name that is unique to this component. Now what this name does is basically it is an attribute that is stored inside the object, and every time I activate this component, it will first delete everything that was baked with that name before, and then it will replace it with the new geometry. So that way you can make sure that whenever you make some changes, you can just hit activate and you will just get only the right geometry and not the wrong one, because the wrong one is being removed for you when you did the bake. So that's one function of this bake name. One of the other functions is to easily reference the objects back into a Grasshopper session. So using the reference by bake name component, which is called ref bake, you can simply specify the bake name of a set of objects. And as long as these objects are actually present in this model, be it in a work session or live in this active model, Elefront will find it for you. So basically this is now a preview of the objects that are baked with the bake name envelope facets. Now all of these envelope surfaces, okay, so it's not just a layer and the name. I realize now that I have actually added some attributes to these surfaces. Now that's not the most important part. I did add these attributes, and I can query these objects for these attributes. So I have some surfaces here, and I'm gonna use the get user value component to get the actual value of direction that I stored inside these objects. Now this is a text string, and it basically relates to the layer. So as I explained, there is the X, Y, and rad direction, and I have grids that have the same attributes. So, and I can see that I was hiding some layers in the grids, which is show. Well, anyway, it is finding these grids, and it's not just finding these grids, because if I would have used only the reference by bake name component, it would reference all the grids that are baked with the bake name grid. And the data structure of this operation would give me one list with 73 grid lines in it. But if I reference in by specifying a specific key and value, and I believe I've explained that, the key is basically the name of your attribute, and the value is actually the value of your attribute. So I am now trying to reference in objects based on a specific condition. So for each of these surfaces, I only want grids that belong to the corresponding direction. So for the first envelope surface, so let's just get one item of this list of objects. So this is only one surface. Now if I bring this one in here and I reference grids, you will see that it only references the grids that belong to that direction. So if I pick another one, this is another surface, and the grids that are referenced for this surface are actually the grids in this direction. Now if I do all of them, it basically means that for each surface I will reference the grids that belong to that surface. Now here's a question for you. In the email that was sent out for this lecture, I put some links, very essential links, and the second link I sent was a workshop about data trees. Have you guys taken a look at that? About half of it? Not really? Okay, well, I will try and quickly explain what that is about. So far, do you get what I'm doing? Does it make sense? Is it okay, because one thing that I forgot to mention is that it's not easy. So it's not like, I will show you some tricks and it will be, it's not like Photoshop where you can say, you know this function? It will make your picture look great. Yeah, it's not like that. You really have to know what you want, and you have to be very explicit, because Grasshopper is an awesome piece of software, but it's far from perfect, and it is still kind of in prototyping phase, and I think it will always be in prototyping phase. It's just, as long as you can get it to work, it's fine. And I think it's fine because a building is also always a prototype. There's, when you do a building, it's just going to be built once. That's your prototype, and then it's done. So you can throw away everything you did, and you can start over again. So in that sense, it's not so bad. But it's not easy. So basically, the way Grasshopper deals with information is in three types of structures, and the most simple type is the one object. So basically, when I took an item from the list, then this is basically the most elementary form of data structure in Grasshopper. It's just one object. It's a referenced breb. Now, as I already showed you, if you have multiple objects in an unstructured way, we call that a list. So this is a list of objects. Now, as you can see, there is already an index assigned to this list of objects. It is called 0, 0. This already indicates that it is possible to have multiple lists in one data structure, and that is a very important feature, because basically you can have lists within lists within lists within lists in a data structure, but the only way Grasshopper can identify these is by explicit paths. So the path of this list is 0, 0. Now, if I want to create more lists, I can, for instance, say that I want each of these objects to be their own list of one object. So the way Grasshopper deals with these kind of structures is what they call data trees. And that is kind of because with all these lists of lists, you can kind of compare to branches of a tree. So you could, for instance, consider this like the stem of a tree, like the core. And if you graph the tree, you can basically split all these objects up into their own little lists. So when you graphed it, you can see that all of these objects are now part of their own list. So these are lists of only one object. But if I would, for instance, divide a surface into 10u and 10v points, you will see that I had lists going from 0, 0, 0 to 0, 0, 6. Now when I divide these surfaces, they will automatically build their own little lists, going from 0, 0, 0, 0 to 0, 0, 0, 6. Well, even it's a little bit more complicated. Let's set this one to 1. just to not confuse you guys too much. That didn't really help. But anyway, as you can see, there are now lists within lists. Now, the best way to actually see what's going on with your data structure is to use the parameter viewer, which has a little tree icon. And if you hook anything up to here, it will show you what the data tree structure is. So this is data with one branch, and there are n is 7, means there are 7 objects in this one branch. Now when you graphed it, there are 7 branches, each branch containing one object. If you double click this component, it will actually show you the tree as a visualization. So basically this is 0, 0, and then each branch basically got its own index. So when we did the division, basically what it does is it creates 10 points in the U direction and 10 points, or let's make the 5 points in the U direction and 10 points in the V direction. And that basically creates you 2 lists for each branch, for each object. One list for all the points in the U direction, one list for all the points in the V direction. And therefore, the tree structure of this guy has 42 branches. Now I'm going to simplify this because there are so many zeros and we don't really need all those. When you look at these paths, you can basically see that the first index of this branch path is running from 0 to 7, which indicates that those are our surfaces still. Now each surface basically has now 6 branches, sub-branches. Is that right? Going from 0 to 5. Yeah, that's 6. So 7 times 6 is 42. And now we have lists within lists within lists. Now we're not going to divide these surfaces. This was just to illustrate that it is kind of important that whenever we reference in these grid lines, we got to make sure that we only have one direction specified for each of these grid lines. So therefore we grafted the tree of these envelope surfaces, because for each of these surfaces we're going to expect multiple grid lines. So if you were to not graph this thing, it would basically, what Grasshopper will do, if it's performing an operation where one input is a list and the other input is also a list, it will perform the operation on the first object from the first list and the first object of the second list, and then the second object of the first list with the second object of the second list, which is often not what you want, because we want the first envelope to be intersected with all of these grids and not just the first one. Now that's a Grasshopper thing. I didn't invent that. Sometimes it's a real pain, but if you know how to deal with it, it's alright. So what we want to do, we want to graph this, we want to make sure that for each branch we get a bunch of grid lines. So if I were to look at the data tree structure of this reference object, you will see that I still have 7 branches, one for each envelope surface, but they have like a different amount of grids being referenced. Now we can already see that the second one has fewer grids referenced. So that would probably mean that the second branch is referencing in these radial ones. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's those ones. Now, by keeping our data tree structure neat like this, we can basically perform all these operations on all the objects at the same time, which makes this way of working very flexible, because if you want to decide to add another chunk to your building, you can just like add a few more of these envelopes, and Grasshopper doesn't care. It will just read them all, we'll just perform the same operation on all of them, and it will just like give you the right output anyway. So what I'm doing, I'm getting these grids, I'm getting the attribute that's called direction, which will basically tell me what direction these grids should be extruded in. And well, la-di-da-di-da, that's my direction. I'm gonna make it 150 meters. So when I extrude all these lines, 150 meters is more than plenty. These are my extruded surfaces. Now, still keeping this data tree structure in mind, I still have my envelope surfaces, 7 branches, 1 envelope surface per branch, and I have my extruded grids, 7 branches. Now, if I intersect my envelope surfaces with the grids, I get these vertical lines. Now, I did the same thing for the horizontal grids. Basically, that's these guys. That's the ones that define the levels for me. And I'm doing the same thing. I'm reading the direction, and I'm extruding these grid lines like this, and I'm intersecting. Now, sometimes Grasshopper does something to the output of these components. And it will basically, because you can have multiple inputs on input A and multiple inputs on input B, it will automatically graft the objects inside of here. And it will basically multiply the number of inputs on the one input with the number of inputs on the second, what we call input parameter. And therefore giving you many more branches. It will basically allow only one output object per branch, and it will, as you can see, there is only 7 objects going in here, but there is 159 objects going in here. It will create 159 branches. Now let me see, am I going to regret this? Not really, but this is also not very important. Now, when we have a look at this data tree, we will see that the 159 branches don't make so much sense to us, because what we want to do eventually is we want to split these surfaces with these curves. And in order to do that, we have to make sure that Grasshopper knows with which curves to split these surfaces, and therefore these data trees are very important, because still we know that we have 7 branches, 7 envelope surfaces, and we have 159 branches here. Now, I'm going to simplify this guy a little bit. If you have a close look at the indices of this data tree, you will see that the first number here still corresponds to the 7 surfaces of your envelope. And the other one is just basically multiplication of the input that we were giving it here. So basically this would indicate that we have intersected envelope surface 6 with 24 other lines. So if we're going to have a look at this, actually Grasshopper is 0 based in its indices, so basically the first item in the list is called item 0. So when you look at this and you will see that this is index 24, it actually means that there are 25 objects doing this. So when we have a look at this, we can see that the last surface, surface 6, is actually being intersected with 25 objects. So if we're going to have a look at surface number 1, you will see that surface number 1 will only go as far as index 1, 8. So I know it's very theoretical, it's very boring, but if you ever have a problem with your Grasshopper definition not doing what you want it to do, 99% of the times it's because of this. It's because Grasshopper will graph this thing, and I'm not sure if I should do this, but if you're not aware of this fact, you will basically just say, okay, intersect these envelopes with these grids. This is my outcome. Now split this envelope with these grids, and the result will be either your computer crashing or totally unexpected and undesired. So I'm not sure if I want to show you how my computer crashes, but I also feel that you should know what this looks like if you're not aware of this. So this is my surface and this is my result. Okay, there's no crashing. But also you can see that the result is not at all what we were expecting. So if I would bake this guy, then you can see that, okay, there's some nice splitting going on here, but it's actually not nice because each of these surfaces is just like split once, and it's a total mess. And you can scratch your head and think, what did I do wrong? I have my curves, I have my surfaces, why did this split not work? 99% of the times it is because of your data tree structure. So in order to get this to work, you want your 7-branch tree back. Now the good thing is your 7 branches are inherently still present in this data tree. The only thing you need to do is shift the path to get rid of the last index. So therefore there is a component called shift path, and it will actually allow you to specify by how much you want to shift these indices. Now this one is specified by -1, so only the last index is going to be removed from this data tree. And the result is going to be your 7 branches back. Each branch now containing just the curves that are the result of this splitting operation. So as you can see, branch 6, even though this surface was intended to be intersected by 25 grid lines, it actually only gave 11 results. Now we can have a quick look to see why that may be the case. Now we can see that branch number 6 is in fact this surface, and as you can see, it's being intersected with all of these 25 lines. So the result will only be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 lines. Is that right? That's right. So these are the 11 lines, and the rest is just not there. So if we look at the ungraphed, if the unshifted list, you will see that for these last lines, there is just zero result. Only these give results. Now when we shift this path, this tree, we basically lose that information. So we now no longer know which of these input curves actually gave us a result. That's why this grafting is happening automatically by Grasshopper, because sometimes you want to keep this information. Sometimes you want to know which of these grid lines actually gave you a result because you have an attribute assigned to this grid line or whatsoever. In this case, we don't care about that. We only care about the data tree being right. So we have shifted this intersection, we have shifted this one. So now we have the vertical grids, and we split these envelopes with the vertical grids, and this is the result that we were actually expecting. All of these surfaces being split by the right curves. Now the result is still a 7-branch. Is still a 7-branch tree. Basically, each branch containing all the surfaces that are a result of this split. But if we want to intersect these surfaces again with the horizontal grids, we're going to have to do some matchmaking again. Because as I told you before, and this is not really Elefront, this is just basic Grasshopper. So that's basically why I actually said you should look at this tutorial on data trees, because without it, there is actually no way you can understand any of the things that I'm about to say. So I hope that I can go through this a little quickly. For the people who joined us later, I'm recording this session. So if you have no idea what I'm talking about now, perhaps later on, if you feel like it, you can watch it again and see if it makes more sense. I will also share these files with you, so you can go over them and see what's going on. As I specified before, we now have 2 trees with 7 branches. But what Grasshopper will do, if I were to intersect these surfaces with these grid lines, it will take the first surface from this list and intersect it with the first curve from this list, and so on and so forth, until it hits curve 14. and then it will just like keep using the last curve, like curve number 14, with the rest of these surfaces. So if I were to do a surface split, and now that I know it's not going to crash, I will show you again, because you will run into this problem probably many times. I have these envelope surfaces here, and I have these horizontal grids, and if I perform these splits, of course now it's not going to crash. It's going to preview this nicely. This looks alright, and maybe the last version of Grasshopper actually makes this alright, but my bet is that it's actually not alright. My bet is that all of these surfaces are only split once. Alright, well that's awesome. So somehow, and I haven't used the latest version of Grasshopper actually. I've only installed it like last week, but this is kind of really nice. And well, there is not much difference from what I was intending to do. As you can see, this operation took 3.3 seconds, so if you're doing the matchmaking, it will also take 3.3 seconds. And I think it's just still because we saw that in this previous example it was just not doing it alright entirely. You may want to keep this in mind. What I'm doing here is basically I'm grafting this tree into 102 branches, and for each of these objects I'm duplicating the branch that belong to it. So I knew, and this is a little bit abstract, I know there are 26 objects in my first branch, and I want to intersect each of these objects with all of these objects from this first branch. So I'm going to duplicate this branch 26 times. Now that's what this component is doing. It's not up to date. I could, but it doesn't really matter. Basically what this component does, I call it graft parallel. So I'm grafting this tree and I'm grafting this tree in parallel, but each of these branches is duplicated. I have, as a result, 102 branches. The top one is each surface, one time. And the bottom one is all the grid lines per each surface. Now if I split that, I get the same result that I got before. Because of the new Grasshopper, is pretty awesome. I get all of these surfaces. Now, I want to just, like, for the sake of demonstration, okay, I want to now know what level these panels are on. So I basically find the center point of all of these panels, and I'm going to project these onto these horizontal grid surfaces. And these horizontal grid surfaces are extrusions of these grid lines. Now these grid lines, they all have a name, because I assigned that to them. So there's level 26, 24, as you can see they're in random order. But of course in real life they're in the absolute correct order. Level 22, level 24, level 26. So they're sorted. So when I project these points onto this surface, this project component in Grasshopper will actually try and project the point onto the first surface it encounters in the reverse Z direction, downwards. And it will give me the index of the actual object that it hits first. So these are my objects. This is the index. So each point now knows which object of this list it hits first. And since I had a list of objects and a parallel list of the actual name of the object, I can just, from this list, grab the item that this project component is giving me, and it will output for me the actual level. So if I were to place a tag to check if this makes sense, I will place a tag on the center point of this panel, and I will actually make the text of this tag the level of this panel. Now if I zoom in, and it's all a bit mingled, but if you zoom in you can see that these panels are all supposed to be on level 18, these on level 16, these on level 20 and 14, and so on and so forth. So this tells me that the mapping actually went fine, except for the fact that I'm missing all the odd numbers. I don't know why, but that's just how these lines were tagged. So this yeah. So now I have found the actual level of each of these panels. Now what I'm also doing is I am using the envelopes, the original ones, and I'm pulling some of the attributes of these envelopes, so the facet and the direction. And I will make sure that I have enough of these attributes. So basically when I look at my data tree, I know that if I shift this data tree again, so this was the data tree with like each of these panels having their own branch. So I know there's 1400 of these panels. If I shift that, now I have all the panels per facet. And I also know the layer of all these facets. So there are 7 branches, so this is the layer of all these facets. This is what I explained before. I know the names of these facets, and I know the direction of these facets. Now, so I have 7 branches with all this. Now if I cross-reference all of these values of these 7 branches with these 7 branches, basically we'll just multiply whatever's in these like single object branches with all of these objects, and the result will basically be, if I have a facet name here, 1, 2, 3, 4, it will replicate all of these facet names for each of these facets individually. Now that's just some boring data tree matching, but it's really dry and really boring. But once you understand the concept, you can basically do anything, and there's really not much more to it, because the only complicated part about like Grasshopper or parametric design in general is how to keep your data structures aligned, basically. And once you understand that, you can really start doing a lot. So basically now I have 3 attributes defined for each of these panels. For each of these panels I know what level it is on, what the facet name is, and what the direction is. So when I specify the attributes for these panels, I specify the names of my new user-defined attributes, and the names are level, facet, direction. And the values are different for each of these objects. So I have a nice data tree here with 1403 branches, because I know that my panels are actually 1403 panels. Can you see that? Yeah, you can see that. So if I have 1403 branches for the panels, I need 1403 branches for my attributes. But instead of it being 1 object per branch, it's 3 objects per branch, because all these 3 objects belong to 1 panel. So I know for the first panel that it's on level 26, that it is on facet 1, and that the direction is X. So now that I have that, I can bake my panels. So I'm gonna delete what I just quickly did, and it will also bake it to the correct layer, which is what I was just showing. So now if I hit activate, Elefront will bake all these objects to Rhino. Each object is now on its own layer, on the right layer. So when we look at the properties, this is on the envelope radial, this is on the envelope Y, and this is on the envelope X. Now if I were to look at the user attributes on this object, I can also do that in Rhino. I oftentimes do, actually. I can just type get user text. When I type get user text, it will ask me which key, like which name, or if you hit enter, you will get them all. So I hit enter, I will get them all. and will basically tell me the bake name of this object is panels raw, the direction is X, the facet is 4, and the level is level 22. Now if we do the same thing for this guy, it will tell me the level is 24. The facet is still 4 and the direction is X. If I would do it here, it will tell me the direction is radial. The facet is 3, but the level is still 24. Here the level should be 22. So all of a sudden these are not just surfaces, but these are surfaces that have certain properties that you have assigned to them and that you can use in the next step. So I'm going to save this model, and now if anyone was to open this model, it would not come necessarily with these referenced models, because basically what I did, and I will show you, when you create these work session files, you reference models and you get the chance to actually save that composition of models. So here's the work session manager. It will tell you what files are actually part of this work session, and you can actually save this, and you will save it as a Rhino work session. And it's nothing more than just like a little file that keeps track of which models belong to each other and which one is the active model. So if you were to open a work session file, it will open whatever is open now. It will open the reference models, will open the active model. But if you were to open, and I just saved this model. If you were to open the model that I just created, it will just only open that model and nothing else. So when you're working in a professional environment, like you will at some point in your life, hopefully pretty soon, it's going to be very important that your models are clean, and this is like the cleanest model you can get, because there are no 25 layers, option 1, 2, 3, guidelines, reference lines, points, old version, copies. It's just this, and all of the logic of creating this is captured in your Grasshopper file. And if anything changes, well, maybe we should just change something. I haven't like really tested this, but let's just give it a go. This is my envelope. So let's see what will happen if I would move this out a little bit, and perhaps move this in a little bit. I'm not sure. This may turn south, and I would probably, it would probably be good to make a copy of this file. So now my envelope is distorted, and I will save it. So if I go back to my first stage and I am to reload my work sessions. Oh, this is not the work session file. This is just the model that I just opened. This is my first stage, and if I were to reload my work sessions, again, I haven't tried this. Maybe the grids will do something very terrible. So this is the new envelope. And now what I have to do is I will have to, because I made Elefront in a way that it will not automatically update whenever you refresh your work sessions, because sometimes it will update your Grasshopper session for each work session file that is updating, and it will take forever. So basically this one is still referencing it's basically referencing nothing. No, it is still referencing something, but it should still be referencing the old geometry. Now you have updated your work sessions, you can basically just recompute your Grasshopper definition. And it will take a little while because the splitting takes a few seconds. Now let's see if we were to hide this guy and to press the, well, let's do a little spoiler, a little preview, okay, and then press the activate button. This is now the new design. Okay, so a little something went wrong, probably because of the stretching. These surfaces are no longer connected. But other than that, it actually came out quite alright. And if we look at the attributes on these surfaces, it will still have all of these attributes. This one still knows it's level 14, it's facet 4 and direction X. And this one will still know it's a radial direction and it's facet 3 and level 14. So this way, you know, kind of shows that you should be able to like modify your definition. So this is whatever inaccuracy you see here is because of the modifications that I just like quickly did. I didn't take too much into account, but let's just see where we can get with this. So well, actually let's just see where we can. Let's just first do the original one. So let's not save this. So now that we have actually created the envelope surfaces, the next thing that we want to be doing is let's see, we want to add some more attributes to these surfaces, just because, and then we want to create a schedule of these panels. So basically, let me have a look. The attributes that I am trying to gather here are a name for each panel, the type of each of these panels, and then there is the width, the height, and the plane that defines like the orientation of these panels in the center of these panels, and I will show you later on why I think that is important. Now the type of these panels we don't know yet, but as I've shown before, we can actually do some data mapping here. So what I did was I prepared a separate model that I have called types, and it is like a simplified version of the model. And all of these surfaces, they are just like put on a separate layer. So there is a layer called spandrel, vision, parapet, and louver. And each of these surfaces is on one of these layers. So now that we have all of these panels, we can reference them back in. And it doesn't matter that it's a work session, because Elefront will also work through work sessions. So I'm referencing everything that's panels raw. I am trying to figure out what all the facet names are. So I'm getting the facet names, but I just want to know the facet names one time. So these are like a lot of numbers. I only want to know the numbers one time because I want to group everything per facet. So therefore I use the set, create set component. It's a very useful component. It will basically return only distinct values, only unique values. So it will basically purge this whole list of numbers into the numbers that are unique. 1, 2, 3, 4, 5, 0. Now it's in a little bit of weird order, so I'm going to sort this into 0, 1, 2, 3, 4, 5, 6. So I'm gonna reference these raw panels again, but now I'm basically gonna filter them per facet. Now whenever I specify a specific attribute name, it will create a separate branch for that. So I know that there are 7 facets in here, and so the result of this reference operation will give me a tree with 7 branches. And now each of these branches contains all of the panels that belong to a single facet. Now I'm going to filter this tree a little bit further, because I also want to find all the levels that are here. And I do that the same way. So these are basically all the levels per panel. So there are a lot of duplicates. And now these are all the levels, basically the distinct values. And when I sort them, these are all the levels that are possible. And now when I'm going to filter this data tree based by these attributes, I'm going to create a tree within a tree. So there are 7 branches, basically 1 per facet. And now when I filter them by how many levels? 14 levels. I can have these 7 branches, which I will simplify this a little bit so you can see it's just 0 to 7. That's going to recompute the whole definition. So 0 to 7, and then I filter it, and now each of these, I'm going to simplify that again. It's going to again take a couple seconds. It's my poor little laptop. It's running out of memory. So now I have for each of these branches, again, 14 sub-branches, 1 for each level. So now I can see these are, whatever is in one branch is on one facet on one level. Now if I want to have a look at what that looks like, I can have a look at one of these branches only. So I can go to set tree and get the tree branch component, and I only want to see path 411. So I type in a panel 411. Now this is my branch, and if I feed it in here and I preview this, it will show me just only these panels. So this is one branch. It means one branch is all the panels on one level on one facet. Now if I want to name these panels, that's exactly what I want, because I want to name them basically from left to right, 1, 2, 3, 4, 5, 6, 7. If I would not have done the filtering per level or per facet, I would basically have all of these objects directly filtered by level, my data tree structure changes a little bit, but if I were to take number 9, the result would be all the panels on one level. And if I were to start numbering them from left to right, it would be 1, 2, 3, 4 all the way around. It makes no sense. You want to have that like separated per facet, so that's why I do this filtering thing twice. So when you have these lists within lists within lists, you can start operating on each of these lists at the same time. So therefore I created like a little cluster. If you don't know what a cluster is, look it up, because they're very useful. It's basically if you have a bunch of objects that are doing a certain thing, you can turn them into your own component rather easily. And you can like copy it around your definition, and if you change something in one, then it will also change into all of the other instances of that cluster in your definition. Now, basically what I'm doing is I'm sorting these objects from left to right. So I'm reordering the objects within my data tree, but the data tree is still the same. It's still 98 branches with all of these containing like all the panels on one facet on one level. And the reason why I do that is because I also create a bunch of names. So I basically have another cluster here. Basically what it does is it will read the length of each of these lists, and it will generate a text saying la-di-la-di-la, and it will have a suffix number basically based on the length. So these are just text strings, and these will now represent the names of these panels. So it will basically, the name will contain the facet in which this panel is a part of, the level at which this panel is, and then from left to right 0 to 12. So this will be facet 6, level 26, and so on and so forth. So that's just a bunch of names that I generated. Now what I also did was find out what is the type of this panel? So basically now that I have all these panels, I can find the center point of these panels, and I can then find the closest surface out of this whole bunch of surfaces that I can see here now. And when I find the closest surface, you can see that this is still a reference B-rep. It is still a reference of the geometry that is in this type model. And if I have that, then I can, what more am I doing with it? If I have that, I can grab the attributes, the Rhino attributes of this object, in this case the layer. So these are all type spandrel because they're all on this brown area, and so on and so forth. So if I were to put a tag of that onto these center points, you will see that this is all vision, and these are now marked louver. So these are now attributes that I have mapped into a similar data tree structure. So basically the attributes are not yet a part of these panels, but they're in the same data tree. You have 1403 of these attributes now, and there's also 1403 panels, so I can just like keep these data tree structures the same all the way to the end. So I have the type now, I have the name. Now what we also want to add is the width and the height, and therefore I'm creating a plane. So I'm taking the center point of each of these panels, and for each of these panels I'm then finding the closest point of the center point. It will give me a UV coordinate, like a local coordinate on that surface, and if I evaluate that surface at this coordinate, it will actually give me the direction of the surface at that point. And from that direction I can actually derive some vectors. You can look into this. Cross product is basically it's a fancy thing. If you take, for instance, if you take the cross product of the x and the y axis, the result is going to be the z. If you take the cross product of the x and the z axis, the result will be the y axis. It's mathematics, but it's very useful to actually find the planes that lie on these panels. So now the x-axis of these planes is always pointing right. No matter where you're looking at, it's always pointing towards the right, because the normal of my surface is always pointing outwards. And when I take the cross product of this outward direction and take the cross product with the z, which is upward, then I will actually get the x-axis in the other direction. I don't know how better to explain it, but then if I take the cross product of the x-axis with the normal of the surface, I will actually get the y. So this will generate me these planes, which is really nice. If I have this plane, I can get the actual dimensions of the object, because you can see what is the width of an object depends on like from which side you're looking, right? If you want the width of this panel here, or of this surface, and you take it from this direction, then the width is completely different than when you take it from this side, which actually makes much more sense. So in order to get the dimensions of an object, you would need to define from where. In this case, that's going to be the plane. Now I can take the object dimensions based on this plane, and it will give me a width and a height. So I have a width, a height, and a plane now. Now I convert this plane into a string because I'm going to save that plane into the object, because we're going to use it over and over again. So la-di-la-di-la, there is some matching here going on. Basically I merge all the keys that I want to save with these. So I already had some keys from the original objects, and I'm going to merge them with the new keys. And I have level, facet, direction, name, type. Oh, level again, that's bad. Facet, direction, okay. So there's some duplication going on there. And then with height and plane. Now as long as these values are correct, it doesn't really matter that, yeah, it's just duplicated, but it doesn't matter, we'll just override it. So let's just leave it at that for now. So this is my referenced model. And actually the color of my object is going to be the color of the type surface that I found. So basically this was my input model, And now if I bake the new model and I hide the input model, you will see that this is the new model that I just baked, and it will have the colors of the type, but it will have all the attributes embedded in it. Now that we have this, it may look like a boring model, but there's already a lot of information in here, and it's more than plenty to convey a lot of design information to whoever. In this case, you're all going to work for a contractor, so am I, and the contractor will want to know metrics of this model already, because even though there's not much detail in here, there's a lot of detail that is already here. So we don't know what the detail between these panels is, but we don't really care at the first go. We just want to know like how much quantities. And now we have it. So basically, if we reference all these named panels which we just baked, if we reference them all in, just update this component, you will see that there's all these attributes here, and by creating a set, we can actually see what the attributes are that are in all these panels. Now, if we want to create a schedule, we may not want to have all of these attributes in the schedule, because the contractor does not care about direction. Direction is something that we need for our modeling. The contractor doesn't need it, so we don't want to report on that. The facet may be useful. Height for sure, level for sure, name is fine. The plane, contractor doesn't care about. What plane, what, no matter. We don't want to report on that. But the type and the width we do. So I just basically copied that list and removed whatever I thought was not necessary. And I have a little component here, and I will share it with you. It's not much. It's a write user value component. This is a little cluster, and it's doing some blah blah. But it ends with something that it ends with a little VB or a little C# component that I wrote that basically like takes this information and writes it to what is called a comma separated value file, and it's basically an Excel file. So I will share that with you. What this component basically does is it'll allow you to feed objects in, specify the path of the file that you want to create, and then specify the attributes that you want to report on. And so this is going to my documents, and if I hit write, it's really fast. It's already done. Let's have a look in my documents, and here it is. So this is a CSV file. If I double click it, it will just open Excel. And this is just a list with all of these attributes for all of these panels. So there's a name, what facet is it on, what level, and so on and so forth. Now, this is nice, but it's a huge list, and a contractor may be bored by it, and it will not fit on your sheet. It's not really great. But you can use pivot tables. This is a Dutch version of Excel. I don't even know how it got on here. I apologize for that. I didn't even know that. So I even have to look at what is a draaitabel. But anyway, we're going to create a pivot table. So it's in insert pivot table, and a pivot table will basically automatically select all these all the values in this table. We want to create it on a new sheet, and a pivot table is Excel's way of reporting. So for instance, we can report on facet, and when we select that, it'll actually show us the sum of the facets. So it will basically count all the values of facet and then report it. Well, that's not really useful. These are, for instance, all the names of the panels, and these are, for instance, all the levels of the panels. Now, if we were to like remove the name, and this is in Dutch, it's just so unfortunate, and move this facet attribute to rows, it will create labels for each of these facets. And now if we were to count the names of the objects on these rows, we don't want to show this in names, we want to show this in count. It will show us this is the count of names for these rows. And now we know that on row 0 we have 168 panels. And on row 1 there's 351 panels. This is not rows, this is facets. Sorry about that. Yeah, it's called facet. We should call it facets. Makes more sense. So facet 0 has this, and facet 1 has the most, basically 351. Or we want to know. So let's create a copy. I hit Control A for everything, and I create this pivot table here now. And instead of reporting on facets, I want to report on level. So these are the levels in my model, and now I can tell you exactly how many panels I have on each of these levels. So it's really easy. Now let's do the same thing, but show me the width. So this is the width of all of these panels. So there's quite some variation. Let's do it with height, because there is more. It's easier with height, I think. There's less different ones. Okay, so we can see that a height of 3800 will happen 811 times. So you can quickly see the variation. And maybe I can sort this thing. I don't even know how this works in Dutch. Well, anyway, you can see that in terms of different types, it's very easy to quickly see how many different types do I have. If you compare the height and the width, and perhaps you can probably even do both. So a width of 600, and we can also it's very small. Well, you can lay this out in many ways, but if it has a width of 600 and a height of 2400, there's actually 51 panels of that. So it's an easy way to create schedule that is actually very meaningful. Does this make sense? Do we think it's useful? Yeah? Okay, good. Because I understand sometimes it's a little boring, but imagine what you can do with this once you really understand it. There's just so this is only like the first step, tip of the iceberg. So we have this. I believe I already baked it. So let's just save this model and let's do some drawings. Are you ready for drawings? It's already 8. Do you guys want to a quick break, or you want to quit, or you want to see drawings? Drawings? All right. So, and this is basically where my preparation stopped, because as you can see, it can take quite some time. So this is where the live part is actually going to start. So this is the model that we just generated, and I want to do some simple drawings. I want to do some overall dimensions, all the way around for each of these panels. Now the first thing I want to do is I want to lay these panels out flat on my XY plane. It's going to make it easier for me to assign, do all this drawing stuff. Now what is a good thing? I have all these panels here. I reference them back in by their name panels, nickname, bake name, and I get the attribute plane, and I use the string to plane component that I will give to you. And I have to recompute. And that will give us all these planes that we so carefully generated in the previous round. By the way, Grasshopper can do some conversions for you. So if you want to know the center point of this plane, you basically can feed the plane into a point component. It will just give you the center point of the plane. That's an automatic Grasshopper conversion. If you would feed that into an XY plane, it will basically like create an XY plane on all of these points. Now we're not going to do that, but so here are local planes. Now basically I want to orient all these panels onto the XY plane. Now I think we all know the orient principle. You like orient 3D, you specify center point and then 2 directions, and then you specify a point in 2 directions on another plane. We'll just move the object there. So we have a whole lot of planes, a whole lot of panels here, a whole lot of planes, and we basically want to orient each of these panels onto the XY plane. And therefore we need a whole lot of planes on the XY plane. So basically what I'm doing is I count how many objects are in here. Now one thing that I should explain to you is that when we did this, basically we have a data tree with 1403 branches. If I would count, if I would use the list length component and I would feed it in here, it would count the length of each individual list, which is 1. So that's not really going to help us. So it will tell us 1, 1, 1, 1, 1. The list is just 1. Now because we don't want that, we want actually the length of the entire tree, what I do is I flatten this tree. And flattening is something that you should very carefully and sparsely do. Because basically what it does is it will destroy your data tree structure. But in this case, that's just what we want. We just want one single list with all of these objects. So if I were to explicitly do that, flatten the tree, it will give me one branch with all of these objects. Now the length of this list is 1403. So I'm going to create 1403 points, and I don't want them all on the same in the same space. I want them to be arrayed from left to right. So I'm going to create a series of numbers starting at 0 with 5,000 spacing, and it's going to be 1403 points. So if I were to look at my top view now, you can see that there is like really 1400 points there. They're spaced 5,000 millimeters from one another. And I feed that into the XY plane, so now I have 1400 planes. So these are my target planes. Now I had my local planes already on my 3D model. So basically all I have to do is grab my panels and orient them. And now they're oriented on my XY plane. There's a lot of them. Now I want to dimension these all the way around, just to like show you the principle. So in order to do that, I take the okay, this is cheating. I already created a component for that, but that's too easy. I'm going to show you how I want to do this. So I'm going to explode these panels, and I want to dimension these vertices, the corner points. So each of these panels was in its own branch, and now each branch has 4 objects, which is 4 corner points. But I want to make sure that these corner points are sorted in the right way. So therefore I'm going to sort them along the edge. The edges are exploded too. So I have to join these edges and hope that they're actually all aligned the same way. So when I do sort along curve, I can now sort these vertices along this curve. And if I do point list, it will show me what the actual order of these points is now. And they all seem to start at the top left, and they all seem to go, not all at the top left, but that's alright. They all seem to go clockwise, which is what I care about. So they go clockwise. So that's already done. Now I have this little component that will do it for you. You specify the vector that is not in the same plane, in this case the z, and it will sort these points for you, and it will make sure that the direction is always clockwise. So in this case we can just go with this because it's fine. So we have a list of points, and we want to draw a dimension line from this point to this point, from this point to this point, from this point to this point, and this point to this point. The dimension component will get the same inputs that you would use when you would dimension this manually. The start point, the end point, and then whether it should be aligned or in a certain plane, and the offset from these 2 points, and a dimension style. So that's the input of this. So this is Elefront component, and if you hover over these inputs, it will tell you what it needs, a dimension offset. So the first point we have, that's easy. The first point is basically like the points that come from this input. But the second point should actually be the next one in the list. So we should shift this list over a little bit. And we shift it over by 1. And when we wrap the values set to true, it means that the last item will become the first item in the list. Well, as a matter of fact, that is exactly what we want for this. So the first point will be the original point, and the second point will be the next point in the list. So it's taking a little while because I'm previewing, and it's 1500 panels. Maybe I should do it on like a little bit less panels first, because it will take a second. And I have like an ultrabook. It's not really made for this. So I'm going to close some models. Oops. Should have undone that. So types, so this thing we can get rid of. So let's just like split this list into, let's just do it on 50 instead of 1500. It's just because my laptop is not used to this brutal force. So I'm going to flatten this list and split it into 50, and I'm going to graph this. So now I have a tree with 50 branches instead of 1400. That should make it a little bit easier. Now the offset is set to 0. I'm going to set that to like 200. And then it's always a gamble like what side it's going to offset to. But in this case it's the right one. If this were to offset to the inside, and then all you have to do is basically just like type negative 200. Then I'll put the dimensions on the other side, which is not what we want to do now. So there you go. So if I would just like right click this and bake this, it will actually like add these dimensions already to the document. So that's the quick way. But you can also set a style, dimension style. It's set to millimeter small. What happens if I set it to millimeter large? kind of makes more sense. So when I specify the style of this dimension, I can actually type millimeter large. Of course, you can make this whatever style you have defined in your document, you can use it. And you can basically also, this can also be a data tree. So if you want each of your dimensions to have a different style, you can just feed like 10,000 different styles to it. Doesn't really matter. So now if I were to I have to delete this manually because I didn't bake it with the bake component. With the bake component I could just bake, and it would just like, it's easy. But I didn't do it. I used the Rhino way, and now I have to like delete it manually. So let's actually use the bake component. So these are dimensions, use the bake component, and I call this temp dim, whatever, as a bake name. Now I activate it. They are now all dimensioned at the millimeter large style. And this will also tell me that 200 is probably not enough. Let's make that 400 and then bake again. There you go. Now you can tweak this dimension style you want. That's just Rhino. Now maybe we also want like angular dimension. So using Elefront annotation, angular dimension. What you'd need is the center point, the point in one direction and a point in the other direction, and it will create the dimension, like in between, the smallest one. So basically we have the center point and we have the next point. Just what we need is the previous point. So this one was shifted 1. Now if we shift this one -1, that should give us the previous one. So this is the point 0, and this is the point 1, and this is point 0, point 1, point 2. This will tell us the center, first dimension, the second dimension. Let's see what that gives us. Well, that's not quite what we want. Center, next point, this is the previous point, next point. Offset of 200. This is kind of let's see. It's actually doing that. That would kind of indicate that I'm doing something wrong. I am doing something wrong. That's point 0, point 1, and that's point 2. This should make more sense. It does make more sense. So now we have an angular dimension right there. And I also want that style to be millimeter large, which is way too large. So I'm going to edit the style and make that 1 to 20. Much better. So that will give us all these dimensions. Now these dimensions, as you can see, I can also just bake them with the bake component, which means that I can also bake them with attributes. Now in this case, I know that these dimensions, all of them, are still arranged in 50 branches, so they still belong to their original panel. So just the easy way to do this is to grab these 50 panels and get the attributes of these panels. Now, it's easier if we would have the right panel for each of these dimensions, because then we can grab all of the attributes of this panel and bake them to each of these dimensions. So I have linear dimensions, 50 branches times 4, so I would actually also want 50 branches times 4 of these panels. So these panels, 50 branches times 1, so I'm going to use the longest list component, and I'm going to compare the list of my linear dimensions to the list of my panels. And then I will duplicate these panels to match the initial list. So I have 50 branches times 4. So basically this panel is duplicated because this one panel has 4 dimensions. So these 4 dimensions all have the same panel. So therefore I'm duplicating this panel. And then I use the get user attributes component that is actually hidden in the Elefront category in attributes. Get user attributes. I get the user attributes of these panels. Now, what this will do, basically, because we have multiple attributes per one panel, therefore it will have to graft this tree, and it will automatically do that. In fact, it should automatically do that. Oh. But of course, I should use this one. So this is my list, and if I put it in here, we'll automatically graft it into 200 branches. And therefore I'm gonna graph my linear dimensions also in 200 branches. So let's move this out of the way. It's gonna get messy now, I apologize. So my linear dimensions, I'm gonna graph them into 200 branches. And I have 200 branches of attributes. So I'm going to feed the keys into the keys and the values into the values. And I'm gonna set a layer called dimensions. And well, I don't really care about the color. And then I'm gonna feed the attributes in here. Now when I bake this, like it will not look like it's much different. When I bake it, nothing changed, except for in my layers there is now a layer dimension. So let's undo this. So whenever you're trying to bake to a layer that does not exist in your Rhino model, the layer will automatically be created by Elefront, and it will now put all of these dimensions on this layer. And if I select this dimension and try and get the user text, it will tell me that basically all the attributes that were assigned to the original panel surface are now also assigned to these dimensions. So this is the name of the panel, and this will make it relatively easy to filter all these, like reference all these objects back in and export them to, for instance, like DWG. Because they're all assigned to this one panel name, you can easily create, and maybe I should just do it. Do we still have time? Do you still have time? Maybe I should just do it. So I'm gonna cheat a little bit. I'm gonna use the same attributes for the angular dimensions, and it is because I know for sure that I have the same number. There's 200 angular and 200 linear. The data tree is the same, so I know for sure that these attributes will actually match. And I can do that too. What's going on here? Okay, I forgot to graft. So actually, because the data trees are so important, I actually decided to give you a warning saying, hey, the data tree doesn't match it. It's like a note to self. It can also help you, because I'm basically like feeding 50 branches as geometry and 200 branches as attributes, and that's not going to work. I feed this in here, and I do that again. Now I don't get a warning, and now when I get the user text of these angular dimensions, everything will be here. Now what we of course would also want is the actual panel. So what we can do is we have these panels, and I'm gonna get all the user attributes of these panels, feed that into these attributes. I want to make this a different layer. For instance, the layer that was the original layer of the panel. So I'm going to read the Rhino attributes of these panels. I'm going to give the layer to the layer, and the name to the name, and the color to the color, name to the name, and the attributes to the attributes. But then I'm not going to bake the original panels, which are still here in 3D, but I'm going to bake the oriented panels. Like so. And in order to make this a little bit more readable, I will reroute these guys. This is, by the way, just a nice little Elefront component that is called a data description. If I were to change this into panel flat Ramon, just to keep track of it, all of these guys will automatically be renamed to panels flat Ramon. So that will help you tremendously to keep your file readable. Panels flat. So now if I bake this one, it will actually bake these panels on here as 3D geometry. Now you could also take the exterior edges and project them to XY, or you could do a make 2D of these panels. If it's much more complicated, then a make 2D is sometimes very nice to do. So, but I'm not going to go there. You could align this easily. So now that we have that, we can bring in all these objects, temp dim angle, and temp dim, like all of this stuff, and bring it back in for an export to DWG. So I'm going to do a reference by bake name, and basically I know already what my bake names are, because I have this bake name, I have this bake name, and I have this bake name. Now I want to know all of my panel names. Actually, I want to know all my panel names first. So I'm gonna do my panels first. I'm gonna get the user value, which is the name. I know there's only one panel per name, so actually already now I already have this one. And now I am gonna reference by bake name. Okay, let's do this properly. These are all my linear dimensions, as you can see, and I'm gonna filter them by name, and the name is basically the name of the panel. And I'm going to do the same thing for the angular dimensions. So these are my angular dimensions, but now they're also grouped by the panel name. So if I merge all of this together, I'll have my linear dimensions grouped, my angular dimensions grouped, and my actual panel grouped. I'm going to merge that. I'm going to simplify these trees just to make sure that they're all the same, and that I keep the same 50 branches that I like so much. So these are 50 branches, and each branch now contains everything that belongs to the panel with the same name. So if I were to check that, I would check branch number 4 of this tree. actually show me this stuff. So when I make this 5, that's all this stuff. So now I have all objects that belong to this one drawing grouped in one branch. And then I can use Elefront export objects. And these are my objects. So I will put them in the object ID. That's the Rhino identifier for each of these objects. And the folder where to save each of these guys now. Let me just create a folder for that. If it doesn't exist, Elefront will actually create the folder for you, but let's just not overcomplicate it. Oh. So this is the folder where I want my drawings to go. Now I have to specify a name for each drawing. Now that's easy because I have the names right here. So that's going to be the name of the drawing. By default it will create a 3DM, but we would want that DWG. I guess I don't think I have AutoCAD on this machine, but usually contractors, they love DWG, so that's what we usually do. The plane that defines the access system, like the origin, the UCS, the user coordinate system, is what you can define. Now we know that because we have stored this as an attribute in these panels. So here's a panel. Oh, that's actually not true. It is actually not true because that's not the oriented plane. So now I'm gonna cheat a little bit. I still have these original target planes. So I'm gonna cheat a little bit and I'm gonna feed them in here. Now the reason why I can do that is because when I use the reference bake component, it will reference all this geometry in the same data tree structure that we had when we baked it. So that is still these 50 branches. And that's the same order as it was when we baked it. So we know that these planes, they're also in 50 branches in the same order. So I'm cheating a little bit. I'm just grabbing it from somewhere where I shouldn't, but just for the sake of this demonstration, I will use that plane. So each of these drawings will have its origin right at the center of the panel. Otherwise, it would be like a kilometer away from the origin in AutoCAD. You don't want that. So the export scheme would make that what is it called? It's just what you would do when you would do it manually. I think it's called 2004 polylines or something. Now, in order to make sure that's what we want, I will do a quick manual export to a DWG, and then the options will tell me 2004 polylines, and what's going to give me. I don't want to explode it. Polyline curve should be splines with polylines, arcs with bulge arcs, polylines, you can set this whatever, save 2004 polylines is what it's called. So you can set that. And then you have to use a toggle because a button won't work. It's a grasshopper bug. And now if we were to save this, because you guys want to have this file, and now if I toggle this, it will just move each of these drawings to this origin and then do an export to DWG, basically like you would if you would do it manually. It's basically calling the command line and just doing it 50 times. So if I toggle this, it will boom 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 do all these panels. Well, this is boring because they're all the same, but we can do it for 1400 panels, and I'm sure there's going to be some variation. So I set this one to false. And if you look in this folder now, there's 50 drawings in there. So if you'd open them, they would be all there. Now to make this a little bit more exciting, and I think that we should wrap it up because we can go on forever. Some people are already asleep. Let's just only do the panels. Oh, I did not mean for that to happen. Let's just only do the panels here at the curved piece, because they're probably all going to be a little bit different, and we know that they're there because they're direction red. So here you can see like the power of attributes. You can just like specify, just give me only the panels with direction red. I'm gonna lock the solver for a second because I'm gonna hook these guys up. I don't want it to like recompute the whole thing twice. Direction red, unlock the solver. So graph this list and do all of them. Now what I have to do is bake all this. So I'm going to bake these dimensions, I'm going to bake these angles, and I'm going to bake these actual panels. This is not an important thing. It's telling me that this component is now obsolete because these objects were removed, but that's not a real problem. That's actually what it's supposed to do. So now we have all these panels, and as you can see, they're all a little bit different. So that's actually much more exciting. And you still get these dimensions out. These angles are now all different. These are all different. So that is actually a much more exciting exercise. So now, because I just deleted the previous batch, I will have to like recompute this thing in order to like get everything back. It will turn green, and if we are to look at the origin now, and if I run this thing again, you will see that it will now quickly show you all of these panels. Like, how many are there? 140. So there you go. Boom, 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 boom. It's exporting 140 drawings with these dimensions. So you can easily quickly see if like there are no weird things happening. Boom, there you go. Now of course you don't have to do it like in one giant, like from left to right. You can set up your own grid like in a 10 by 5 and just like lay it out on the sheet directly like that. If you just bake it, boom, and you just like put it on a sheet. That can also work if you're doing a schedule. So if we're looking at the drawing folder now, you can see that there is already like 190 drawings in there. And that was rather easy. Rather quickly, and so on and so forth. Any questions? No questions. Do you have any like idea already, like how you could use this for this course on your project? So you may want to think about that. I like this whole process was born out of a necessity for us, and I think that's the right way to actually use software. Normally you're working the way you want to work, and then you encounter something that you think will take you a long time, or you don't know how to do it. That's when you can start thinking about using something like this. Of course, the alternative is you think, hey, I want to impress some guys. I want to do just like 500 drawings on a sheet, and I'm just going to work it from the top down. Of course, that you can also do. That's entirely up to you.